Einstein understood something about light that most people at the time didn't understand. He understood that light comes in little packets, little discrete pieces of energy. He called them quanta, or what we now call photons. That was brilliant. That was revolutionary. But here's the thing, and this is what I find so beautiful about science. Even Einstein didn't fully understand the whole story about light. He missed something, and what he missed is really the heart of quantum mechanics itself. Let me start by asking you a question. I want you to think about this carefully. What is light? Now that sounds like a simple question, doesn't it? But it's not simple at all. You see, if you asked physicists at different times in history, you would get completely different answers. In the 1700s, Newton said, light is made of little particles. Then in the 1800s, people said, no, light is a wave. It's like ripples on a pond or vibrations in water. And they could prove it. They had experiments, beautiful experiments, that showed interference patterns, diffraction, all the things waves do. So light is a wave, right? Well, not exactly. You see, Einstein came along in 1905 and he said, wait a minute, look at this photoelectric effect experiment. When you shine light on a metal, electrons come shooting out. But here's the strange thing. If the light is too dim or too red, nothing happens. No electrons come out, no matter how bright you make it. But if the light is bright enough and blue enough, boom, electrons come out immediately. Einstein said, that doesn't make sense if light is a continuous wave. If light were a continuous wave, the electron should be able to accumulate energy slowly, until it builds up enough to escape. But that's not what happens. So Einstein made a bold hypothesis. He said, what if light actually comes in little packets? What if each packet carries a specific amount of energy that depends on the color of the light, the frequency? He called this energy E equals H times F, where H is a constant named after Planck, and F is the frequency. So a blue photon has more energy than a red photon. This explained the photoelectric effect beautifully. If a single photon has enough energy, boom, one electron comes out. If it doesn't have enough energy, no electron comes out, no matter how many dim photons you throw at it. This was revolutionary. This was so revolutionary that Einstein won the Nobel Prize for this idea, not for relativity. Can you believe that? He's famous for relativity, but they gave him the Nobel Prize for this understanding of light as particles. Even Max Planck, who first discovered the energy comes in packets, didn't really believe in the reality of these photons. But Einstein believed it, or at least he believed it well enough to explain the photoelectric effect with it. Now here's where it gets interesting. Here's where the story gets really beautiful. Einstein understood that light has a particle nature. But what did he miss? He missed, and this is the deepest thing, he missed the full weirdness of what light actually is. You see, he explained light as particles, little packages of energy. But light is not just particles. Light is also waves. And I don't mean that light sometimes acts like a particle and sometimes acts like a wave. That's what people say, but that's not quite right. That's not quite the real mystery. Let me tell you about an experiment. This is one of my favorite experiments to think about. Imagine we have two slits like this. We have a screen with two slits, and behind it we have a detector screen. Now, if I take some bullets and I shoot them at the two slits, what happens? Well, some go through the left slit, some go through the right slit. The ones that go through pile up in two piles on the detector screen behind. You see a pattern like this, two bumps, one behind each slit. The total pattern is just the sum of the two individual patterns. That makes sense. Now, what if instead of bullets, I use water waves? I create ripples on a water surface and I let them go toward two slits. Interesting thing happens. The waves go through both slits and then they spread out and interfere with each other. Where they add up, you get big waves. Where they cancel out, you get nothing. So instead of two bumps, you get a striped pattern. Bands of big waves and bands of no waves. This is interference. This is a characteristic thing that waves do. Now here's the question. What does light do? What happens when I send light through two slits? Well, this is where it gets really strange. If I use a very bright light, a normal light, it acts just like water waves. I don't see two bumps. I see this striped pattern, this interference pattern. Light is behaving like a wave. It seems to go through both slits, and the light from the two slits interferes with each other. But now, here's where Einstein's picture starts to break down. Let me turn down the intensity of the light. Let me make it very, very dim. Now I can detect individual photons coming in. Einstein said light is made of little packets, right? So with very dim light, I should see individual photons coming in, one at a time, like little bullets. And they should pile up into two piles like the bullets do. right? But that's not what happens. This is the most amazing thing. Even with the dimmest light, even when I'm sure that only one photon at a time is in the apparatus, I still eventually get the interference pattern. It slowly builds up into stripes. How is that possible? How can a single photon interfere with itself? That makes no sense. You see, this is what Einstein understood, that light comes in particles. But it's not just particles. It's something much more subtle, much more mysterious. And this mystery is really the heart of quantum mechanics. When you really dig into it, light is not a particle in the way you usually think of a particle. Light is not a wave in the way you usually think of a wave. Light is something else. Light is something that doesn't have an exact analog in our everyday experience. Now, here's another thing that bothered Einstein, though he may not have thought about it in exactly this way. Let me tell you about something. Imagine you want to find out which slit the photon goes through. You want to know, does it go through the left slit or the right slit? Well, you can put a detector there. You can put a light source there to illuminate the photon and see which slit it goes through. You detect whether it's going through the left or the right. Here's the crazy part. If you do that, if you put a detector to watch which slit the photon goes through, the interference pattern disappears. Now you get two bumps like the bullets. The photon behaves like a particle. But if you take away the detector, the interference pattern comes back. The photon behaves like a wave again. It's as if the photon knows whether you're watching it or not. It's as if the photon is shy. If you're watching, it behaves like a particle. If you're not watching, it acts like a wave. This is not just a detail. This is not something you can ignore. This is absolutely fundamental to quantum mechanics. This is the deepest thing about how nature actually works. And Einstein, brilliant as he was, never fully accepted this. He never fully accepted that this was the way nature really is. He kept saying that quantum mechanics was incomplete. He kept saying there had to be something deeper, something hidden, that would explain all this strangeness away. Let me tell you why Einstein thought quantum mechanics was incomplete. Einstein believed in something called realism. He believed that the world has a definite reality that exists independent of observation. He believed that things have definite properties whether you look at them or not. And he believed that nothing can travel faster than light. These are called local realism. And Einstein thought these principles are so fundamental, so obviously true about the world, that quantum mechanics must be incomplete. There must be some hidden variables, some hidden information that explains all this weirdness. But here's what's amazing. Einstein was wrong. Experiments that were done many, many years later showed that Einstein was wrong about this. There are no hidden variables. Nature doesn't have a hidden layer of completeness waiting to be discovered. It's not that quantum mechanics is incomplete. It's that our classical intuitions are wrong. The world really is the way quantum mechanics says it is. And that's both exciting and deeply strange. You know what Einstein missed? Einstein missed the courage to accept nature as it really is. He missed the courage to say, well, nature is not the way I always thought it was. Nature is stranger than that. Nature is more subtle than that. And that's okay. That's beautiful. That's wonderful. Instead, he spent the rest of his life trying to argue that quantum mechanics was wrong, or at least incomplete. It wasn't. It's not. But let me be fair to Einstein. Let me tell you why it's so hard to accept quantum mechanics. Let me give you another thought experiment. This is one I like to think about. Imagine I have a single electron, just one electron. I'm going to measure its position. I'm going to find out where it is. I measure its position, and I find that it's at a certain location. Okay, good. Now a tiny bit later, I measure its momentum, how fast it's moving and in what direction, and I get a certain value. Now, a good scientist, you would think we could predict where the electron will be a tiny bit later by knowing where it is now and how fast it's moving. That's just Newton's laws, right? Well, here's the thing. If you measure the position very, very accurately, you will find that you cannot measure the momentum accurately. The more accurately you know where the electron is, the less accurately you can know how fast it's moving. It's not that you're bad at measuring. It's not that your instruments are not good enough. It's a fundamental thing about nature itself. This is Heisenberg's uncertainty principle, and it follows right out of the wave nature of particles in quantum mechanics. You see, the position and momentum of a particle are not both well-defined at the same time. They cannot both be well-defined. It's not that we don't know them both, it's that they don't both exist in a definite way. They're complementary. Just like in the double-slit experiment, a particle cannot have both a well-defined path and also produce an interference pattern. If you make the path definite by observing which slit it goes through, the interference pattern goes away. That's not because you disturbed it in an uncontrollable way, That's because position and path are incompatible with the interference phenomenon. This bothered Einstein enormously. He said famously to Niels Bohr at a conference something like, "God does not play dice with the universe." He said this as a kind of criticism of quantum mechanics. But you know what? Nature does play dice. Nature is probabilistic. Nature is not deterministic in the way that classical mechanics is. You cannot predict with certainty what will happen in a quantum measurement. You can only predict the probabilities, and that's not a limitation of our knowledge. That's a feature of nature itself. So what did Einstein really understand about light? He understood that light comes in discrete packets. He understood that each photon has energy proportional to its frequency. He understood that this explained the photoelectric effect. This was brilliant. But he didn't understand, or perhaps he understood but refused to accept, that light is fundamentally quantum. That light is fundamentally strange in a way that doesn't fit into our classical categories of waves or particles. Let me tell you what we now understand. Light is neither a wave nor a particle in the classical sense. Light is what we call a quantum object. It has a wave function. It's described by a wave function, which is a kind of mathematical representation that doesn't directly correspond to anything in the real world that you can visualize. The wave function describes all the possible outcomes of different experiments you could do on the light. When you actually do a measurement, the wave function collapses and you get a particular outcome. Before the measurement, the light is in a superposition of all possible states. It's not here or there. It's in a sense both here and there, or neither here nor there. The language breaks down. But here's the beautiful thing. Here's what makes quantum mechanics so powerful and so strange. It actually works. Even though we can't visualize it, even though it doesn't fit into our classical intuitions, it predicts the results of experiments with incredible precision. It's the most accurate theory we have ever had about how nature works at the small scale. Now, I want to tell you about one more thing about light that Einstein probably didn't fully appreciate. Einstein explained light as photons carrying energy equal to h times f, where f is the frequency. But here's something subtle. A single photon doesn't have a frequency in the classical sense. You can't point to a photon and say, this is the frequency of this photon. Frequency is a property of waves, not particles, but a photon is associated with a frequency through the wave function. The wavelength and frequency of the photon come from the mathematical description of its wave function, not from some classical property of the photon itself. You see, what's really happening is this. We describe quantum systems using mathematical waves, wave functions, but these are not real physical waves in space. They're probability waves. The square of the wave function tells you the probability of finding the particle at a certain location when you measure. These are very different from classical waves. A water wave is a real physical wave. Water molecules are actually going up and down, but the wave function of an electron or photon is not like that. It's purely mathematical. It encodes information about probabilities. This might sound abstract, and it is, but that's okay. Nature is abstract at the small scale. We shouldn't expect it to be easy to visualize. What matters is that it works. What matters is that it makes predictions that agree with experiment. So let me come back to my title, What Einstein Missed About Light. I think Einstein missed several things. First, he didn't fully appreciate or accept that quantum systems don't have definite properties independent of measurement. He didn't accept that the act of observing a system actually affects the system in a fundamental way. Not just because of some disturbance, but because the property you're measuring doesn't exist in a definite way until you measure it. Second, I think Einstein missed the deep unity of nature. You see, he thought light was made of particles. But particles have their own quantum weirdness. Electrons are described by wave functions just like photons are. Electrons can produce interference patterns just like light can. They have de Broglie wavelengths. Everything in the quantum world has this duality. It's not that light is special in having a particle nature. It's that all matter and all energy have this quantum nature. They can't be fully described as either particles or waves. There's something in between, something different, something that requires a new way of thinking. Third, I think Einstein missed, or rather he resisted, the idea that nature is fundamentally probabilistic. He thought there must be some hidden layer of reality that brings back determinism, but it's not there. When you do a quantum measurement, you get a random result with different probabilities for different outcomes. There's no way to predict which result you'll get. There's no hidden information that would let you predict it. This is not an approximation. This is exact. This is the way nature really works. And fourth, I think Einstein missed the beauty of accepting mystery. He kept trying to resolve the strangeness, to push it away. But the strangeness is the heart of quantum mechanics. The strangeness is where the truth is. If quantum mechanics seems strange to you, if it seems to violate your intuitions, then you're on the right track. You're beginning to understand how nature really works. Now, don't get me wrong. Einstein was one of the greatest physicists who ever lived. His contributions to physics are enormous. But he was also a human being with certain beliefs and certain intuitions, and those beliefs and intuitions sometimes got in the way of fully understanding the quantum world. It's a good lesson for all of us. Nature is under no obligation to make sense to us. Nature is not obligated to fit into our categories, our intuitions, our beliefs about how the world should work. The only thing nature cares about is working, and quantum mechanics works beautifully. You know what I find most remarkable? Here's what I really want to leave you with. Quantum mechanics is the most successful theory in all of science. It's the foundation for modern technology. Transistors, lasers, solar cells, all of it, all built on quantum mechanics, and yet we still don't fully understand what's really going on. We have formulas that work. We can make predictions with extraordinary accuracy, but the interpretation of what it all means, the real deep understanding of what's happening, that's still an open question. There are still different interpretations, different ways of thinking about quantum mechanics. Some people, like Bohr, thought that there is no reality until you measure something. Others, like the many worlds interpretation, think that every possible outcome actually happens in different branches of the universe. Others try to bring back hidden variables, going back to Einstein's original intuition. But whatever interpretation you prefer, the predictions are the same. The math is the same. The experiments agree. And I think that's one of the most beautiful things about physics. We can have disagreement about what it really means, about what's really going on deep down. And yet we can still use quantum mechanics to build amazing things, to make accurate predictions, to understand the world. That's the power of science. That's the beauty of the scientific method. So, light is quantum. Light comes in discrete packets called photons. But those photons are not classical particles. They're quantum objects, and they have properties of both waves and particles. Einstein understood the particle part. He understood that light carries energy in discrete packets. That was his brilliant insight. But he didn't, or he wouldn't accept the full quantum nature of light. He didn't accept that light, like everything else in the quantum world, is fundamentally strange, fundamentally probabilistic, and fundamentally dependent on observation. That's what Einstein missed about light. But, you know, missing it didn't prevent him from making one of the greatest contributions to physics. It's a reminder that even the greatest minds have limits. It's a reminder that nature is always stranger than we imagine. And that's what makes physics so wonderful. That's what keeps us going, keeps us curious, keeps us trying to understand the deep mysteries of the universe. The real question isn't, what did Einstein miss about light? The real question is, what will we discover next? What else don't we understand about nature? What deeper mysteries are waiting out there? And that's what physics is all about. That's the adventure of understanding the universe. And I think that's beautiful.